In this video, we're going to talk about exponential growth and decay, which is something that we've actually already been talking about, but we're going to look at some other applications that we have not discussed before. As this states, many other quantities in nature change according to an exponential growth or decay function that's given in the form P of t equals P naught times e to the k times t. Now we've seen this before, but maybe we've used the variable r, or maybe we use the variable k as we are here. But this is that same exponential function with the base e. Remember, p naught or p sub 0 is your initial quantity, or the initial amount of whatever your output is, and k is your growth or decay rate. All right, and remember, this is for continuous growth or decay, right? And so once we know P naught, we'll substitute it here. Once we know K as a decimal, usually it's given as a percent, but when we do the calculations, we use it as a decimal. We put that there, and so when we input a T, our input variable T, it'll output the amount after that much time, or the value of that variable has passed. And so in example 1, it says the number of people living with HIV infections increased worldwide exponentially from 2.5 million in 1985 to 34 million in 2010. Give a formula for the number of infections, H, which is in millions, as a function of years, which is T, since 1985, right? And so since we're dealing with exponential growth and decay, of course, it started with 2.5 million and it ended with 34 million in 2010. We know that we have exponential growth. And so with that, remember in this formula here, when we have continuous growth or decay, when K is positive, we have growth. When K is negative, we have decay. So we're in the growth feature here. Our goal here is to be able to figure out what P naught and K are so that we'll have the actual formula here, right? So our goal is to find P naught and K. We're going to use this information that they give us. I know in 1985, that's 0 years from 1985, right? That's our initial quantity, right? So we know that P naught equals 2.5 million. And we also know that when T equals, 2010 minus 1985, that's 25 years. When T equals 25, then we know that our output, our P of 25, is that 34 million, right? This is the same as giving me an ordered pair 25, 34. And on our initial amount, this is like giving me an ordered pair 0, 2.5. So I can ask this question by just giving you two ordered pairs and asking you to find the exponential function that's representative. And you go through this process here, right? And so remember, our goal is to find P naught and K. We already know our P naught. So let's plug in some stuff into our formula. I'm going to rewrite our formula here. Our P naught is 2.5. We know that when T equals 25, so if I replace 25 in our function for T, our output is going to be that 34 million. And so here we have an equation with one single variable. Remember that E is a constant. We can solve for that by dividing both sides by 2.5. We can take the natural log of both sides. And we remember that the natural log and E are inverses of each other, so they undo each other. So we get 25K equals that natural log of 34 divided by 2.5. We'll calculate that later. And then we can divide both sides by 25. And then we're going to get that K is approximately, let's go to our calculator to see exactly what that is. And so I'm going to put this in my calculator. Once again, that's the natural log. Remember, your natural log button is here. I'm going to do 34 divided by 2.5. I close that parenthesis and I divide that by 25, and I get an error because I did that wrong. I did multiplication in there. This should be a division here. And so I get approximately, I'm going to round that to 4 decimal places, 0.1044. And so if I wanted to write my function, I would have that P of t is 2.5 times e to the 0.1044 times t. So this is the formula that represents this scenario here, right? This is my formula. And so let's go to part B. And in part B, they request that we find h of 30. And that brings me to another thing that I'm missing here. See, even your instructor makes some mistakes, right? So I know that my regular function is in P and P naught, but they give us our variables here in terms of H and T. My output variable is H. And so instead of writing this with P, I'm going to present my solution using the variables that were given to me. So this is H of T. Learn from our mistakes, right? And so now we're going to find h of 30. Well, h of 30 is just simply us substituting 30 in for t, our input variable. And then we'll get an approximation as our result, right? And so I'm going to plug in that into my calculator. Now, what I'm going to do is I'm going to use the fact that 0.1044 is not the exact rate. My exact rate is natural log of 34 divided by 2.5 divided by 25. I'm going to use that in my calculator features to help me find my result here. So I'm going to do 2.5 times E. Remember, your E is second ln. They're inverses of each other, so they're using some of the same buttons on your calculator. I'm going to use my answer feature so that I can have this exact value saved. So I'm going to do second, the negative sign. You see that A and S that represents answer. And that's multiplied by 30. And I get 57.304. Sometimes, it may not be the case in this example, but sometimes when I just round my answer here, so let's just see, if I round my answer to just one decimal place, that percentage, and then try to do that calculation, it may not matter in this one, but if I did that 0.1044, I rounded that to one decimal place and try to do this calculation, my answer is, well, it did actually happen in this case. My answer is just really, really different, right? So that's why I want to use this answer feature in my calculator so that I can get as close to the right answer as possible. Because what this answer feature is doing is it's saving all the decimal places are a lot that your calculator uses, at least 9, I believe, for this decimal approximation here. And so that will help us get more close to the actual solution. I think if you did do 4 decimal places, let's just try it out here. It would be fine. But since you have the answer feature, I recommend that you use it. All right, so when we use the answer feature, we got 57.304. When we use the 0.1044 rounded to the 4 decimal places, we basically get that same number, right? And so what I recommend is that when you do these problems, definitely use the answer feature or try to round it as many decimal places as possible. Sometimes 4 and 5 decimal places is good enough, right? So if I look there, that was approximately 57.3. My units to this, remember your output represented H, which is in millions, and that's the number of infected people. So it's going to be million people. And the interpretation here, we can say 30 is 1985 plus 30 is 2015. So we can say in 2015, I got to do that in my head. It's a shame. Yeah. 1985. In 2015, there were approximately 57.3 million people diagnosed with HIV infections. All right, that's an interpretation of what this value actually means, right? Remember, your input is the number of years since 1985, 30 years is 2015, and your output is the number of infections in millions of people, all right? And so that's my result there. So we can use this natural exponential base to model different things, and we can do the same things that we've been doing and solve these problems, right? What we hadn't talked about is some of the more specific applications like compound interest, right? Compound interest is like when you put money or invest money into an account, a bank or some investment firm will give you an interest rate for keeping your money in that account. All right. And so the money that you earn on top of what you put in there is called your interest. There are different ways to compound interest or to calculate interest. And compound interest basically means your interest is calculated not only using the money that you put into the account, which is called your principal, but also on the previously calculated interest, right? That's what compound interest is. And so there are two formulas that we're going to review. There are actually way more than two formulas for compound interest. We're only going to look at two in our course. And one of the formulas is when interest is compounded annually. That means one time per year. You take your initial investment, which is the principal, you multiply it by your growth rate, which is 1 plus r, and you raise that to the t. It's an exponential function here. This r is your interest rate. Remember, whenever we use an interest rate, it's usually given to us as a percentage, but when we do percentages, we usually convert it to a decimal. And t is your time, and we usually always do this as your time in years. All right. And so if your interest is compounded annually, this is the formula that we're going to use. If your interest is compounded continuously, well, we're going to use our natural exponential function, where P naught is your initial investment, which is your principal. R is still your interest rate, but now we have a different base because we're doing this continuously. All right. And so we have this example here. We have suppose $100 is invested in an account with the 4% interest rate. How much money is in the account after 20 years, right? So what these formulas give here, they don't calculate your interest, they calculate your future value. How much is in your account after a certain number of time has passed. Some people call the P naught here, instead of calling it principal, some people call that your present value. All right. So you start with your present value, you know your interest rate, you know how long you're going to have that money in that account. You can use that present value and that information in order to calculate your future value, which is your outcome here. All right. And so this is basically what this is asking. $100 invested at 4%. How much is in the account after 20 years have passed? If interest is compounded annually versus interest is compounded continuously. Well, when interest is compounded annually, well, first of all, let's identify what we're given. This is our P sub 0, our P naught. This 0.04 would be our R, and then this 20 would be our T, right? And so if I want to know how much interest is, how much is going to be in my account after 20 years, I replace T in my formula with 20, P naught with 100, R with 0.04 because it's 4%. And again, that T is replaced by 20, right? You put that in your calculator. Let's do it together just to get some practice on the calculator. I have 100 times, I'm just going to go ahead and put that as 1.04. We're going to raise that to the 20th power. And that gives me, since we're dealing with dollar amounts, $219.11. If I round that to 2 decimal places, because that's how we deal with money in the US. And then here, when it's compounded continuously, 100 times e to the 0.04 times 20. I can get an approximation, so I'm going to use the approximately equal here. I'm going to put that in my calculator, so I have 100 times second natural log for my e, and I'm going to have 0.04 times 20. Note here, when you use this e here, and if your calculator doesn't look exactly like mine, sometimes your calculator will show up with this symbol on the calculator, if you can see my mouse here. Make sure you put the 0.04 times 20 in parentheses, or you're going to get this incorrect, right? But in this case, we get $222.55. All right, and so as you can see, the more times you get your interest compounded, which continuously means it's continuously compounding your interest, you're going to get a little bit more of your future value here. Notice this is a 0.04 here, looked like a 9. All right. What we want to do now is we want to switch gears slightly and talk about half-life and doubling time. Half-life and doubling time are time intervals, right? It's the amount of time it takes for a quantity to reduce. I'm just going to change this up here. To reduce to half its original size. The amount of time it takes for a quantity to reduce to half its original size. All right, doubling time is the amount of time it takes for a quantity to double. Now, I've given these two definitions here for half time and doubling time. Notice you can have amount of time it takes for something to triple, right? That means it's gonna be the amount of time it takes for it to grow to double its size. I mean, triple its size. You can have quadrupling time. You can have how much time it takes an object to reduce to a fourth of its size. I'm just giving these two examples here because they show up most often, but you may see examples where it's more than doubling or half time, all right? Let's look at an example where we apply this in the context of exponential growth and decay. The size of a bacteria colony doubles every 12 minutes. If the bacteria is growing exponentially, how long will it take the number of bacteria to be 5 times its original amount? Okay, so we're given a lot of things and we want to know one thing, right? We're given the doubling time, it's 12 minutes. But we want to know how long it takes for it to be 5 times its original amount, right? So it uses doubling time, but we want to know I know 4 is quadruple. I don't know the word for 5 off the top of my head, but there we go. So it's growing exponentially, and the bacteria grows continuously. So we're going to use the compound interest formula or the exponential growth formula when things grow continuously. All right. If you use R here, R, K here, it doesn't matter. They mean basically the same thing. And basically, what we want to know is how long it would take it to be 5 times the original amount. Well, we don't even know the original amount, but we know it would be in p sub t here. We don't even know the rate here, and our goal is to find t, right? So we're not given much information. All right, the information that we are given is a t here, and the fact that this is the amount of time it takes to double, right? What this first sentence helps us do is to find the rate at which it's growing, all right? And so we're going to use that first sentence and the doubling time, which is given to us as 12 minutes, in order to help us figure out how much time our actual rate, which is K in this formula here. Because we know that if we plug in 12 for T, then our output is going to be twice the original amount. Now, we don't know the original amount, but we do have a representation of it here, which is P naught. So if I start with P naught and I need double of what I started with, then I'm going to end up with twice P naught or 2 times P naught. Now, it looks like I have an equation that has two variables, P naught and K. But since P naught is multiplied on both sides of this equation, I can actually divide both sides by P naught because that's not the variable I'm trying to solve for. So I can do that. And then I have an equation basically with just one variable, which is K, which will help us answer the next part of the question, right? So let's solve this equation for K. Remember, we can take the natural log of both sides. The natural log and the E cancel. We get 12K equals natural log of 2. We divide both sides by 12, and then we can go to our calculator and get an approximation for K, right? So I'm going to do the natural log of 2 divided by 12, and I get approximately that P of T, I'm going to round that to 4 decimal places, 0.0578. So what I have here is that P of T equals P naught times e to the 0.0578 times T. That gives me some information, and I'll submit to you that that gives me enough information to answer the question, even though I don't know P naught, right? It says, how long will it take for the number of bacteria to be 5 times the original amount, right? Well, that means I want to solve for T, and I know when I end up substituting whatever T I'm trying to solve for, I'm going to end up with 5 times the original amount. Well, that's 5 times P naught. So I can do this problem here without having any information about P naught. Again, since P naught is multiplied on both sides, it really doesn't matter here. All right, because I can divide both sides by that P naught, and I have an equation with just T, which is the equation I want to solve for. Let's take the natural log of both sides. Natural log and E cancel. Divide both sides by that 0.0578. And I get that T is approximately, all right, I'm going to use that number, that answer feature again, right? I'm going to do the natural log of 5 divided by that 0.0578, but that's my answer in my calculator. And I get that T would be approximately 27.86, and my units here is minutes, since T was time and time was in minutes. All right, and so this is an example here of doing that. This concludes this video. I'll see you during the next video.